Hi, my name's Jeremy O'Brien. I'm the CEO of PsiQuantum, and I recently gave this talk at the American Physical Society March meeting, and I wanted to re-record it here so that those of you who weren't able to attend the March meeting and are interested in some of the very exciting progress that we've made towards building a genuinely useful quantum computer could catch up on that. So PsiQuantum was founded with the singular focus of building a genuinely useful quantum computer. And at the time, we believed this meant having a route to building a machine comprising on the order of 1 million qubits, so that the miracle of quantum error correction would let us do tens of billions of gates on hundreds of logical qubits. And over the last few years, we have invested all our resources towards a technology which really has a path to that end goal. In other words, we've been investing in rocket engines rather than incrementing on a proof of principle. Of course, an important observation here is that this rocket engine doesn't actually go anywhere. It doesn't even get 1 foot off the ground. That being said, I'd much rather have this thing on the right than this thing on the left. And as time has gone on, we have become increasingly confident this was the right vision. All of the world-changing algorithms known today still require error correction and a large-scale machine. And we are very glad to be in a session at the March meeting where many other people are talking about the challenges of scaling up and building a fault-tolerant quantum computer. Today, I'll tell you about the 3 most important advances we have made towards the goal of building a useful quantum computer. I'll begin giving you an example of the advantages that we have unlocked by pursuing a truly manufacturable technology. I'll then tell you about our unique fault-tolerant architecture, which has significant advantages for photonics. And then finally, I'll show you some important breakthroughs for scaling of the system, which greatly reduce the challenges of building a fault-tolerant machine. So let's start with manufacturing. It's been my conviction for the last 25 years that we won't have a quantum computer in my lifetime unless we figure out how to build it in a tier 1 semiconductor fab, the same fabs that build the billions of transistors in your laptop or your cell phone. And when we founded the company, it was the existence of this science fiction-like manufacturing capability that gave us the confidence to shoot straight for 1 million qubits. That said, it's a widely underappreciated fact that there are really only 3 tier 1 foundries on the planet. And there's really a night and day difference between small boutique fabs and those 3 guys up here in terms of scale, predictability, and performance. The flip side, of course, is that these guys are not in the business of doing fun R&D projects. They are building millions of laptops and cell phones and won't allow crazy materials or exotic devices into their clean rooms. The reason we chose this approach has nothing to do with wanting to build millions of quantum computers, but rather that a tier 1 fab is the only place you can access the most advanced manufacturing tools on the planet. Of course, you can build a handful of qubits in a 200mm R&D line, but our belief is that if you try to build a 1 million qubit quantum computer anywhere other than a tier 1 fab, it won't work, either because of yield or device performance that is insufficient for fault tolerance. And after over 20 tape outs in 200mm lines, we have some hands-on experience of the limitation of those fabs, and I'm happy to report that we have now partnered with one of these tier 1 foundries as our production partner. As of a year ago, we are manufacturing quantum devices in a tier 1 production line. We've put 6 tools into their production line, including a niobium nitride deposition tool to build superconducting single photon detectors, and a liquid helium cryostat for inline detesting of those detectors. And what you're looking at here is a standard 300mm silicon wafer built in that manufacturing process. It has 25 layers in the stack, and there are over 500 process steps involved in getting that built. Each of these wafers has tens of thousands of single photon sources and tens of thousands of single photon detectors on it. And we have now processed over 1,000 wafers worth of material with our production fab. Of course, people have built integrated superconducting single photon detectors before, but what we're showing here is really exciting in terms of scale and especially integration. Let me show you what I mean by that. To appreciate why the transition from a 200mm fab to a 300mm one has been so important for us, let's consider just a single parameter, the line edge roughness, or basically how smooth the fab can make the walls of both our detectors and our waveguides. The line edge roughness directly impacts both the detector efficiency and photon loss in the waveguides. And what we found was that going from a 200mm to a 300mm process gave us up to a 5x improvement in patterning quality. But of course, what really matters is whether this leads to actual superior performance in metrics that affect the functioning of the quantum computer. And the impact on device performance is no more stark than in the single photon detector, where improvements in pattern fidelity and line edge roughness, for example, has made a huge difference in the efficiency of the device. Unsurprisingly, the quality of your processing has a direct impact on the performance and yield of your devices. The smoother nanowire allows us to operate at a higher bias current and results in greater sensitivity of the device. Here's a plot showing how the intrinsic efficiency of our detectors changes with temperature, and the three curves correspond to three different manufacturing processes, 2 at 200mm and 1 at 300mm. As you can see from the bottom curve, our detector efficiency is already very high, and this is for non-optimal detector designs. And here is an image of that device. The devices that we produce are frankly just beautiful to look at. Sometimes you have to do a double take to be sure whether you are looking at the design or the real thing. Of course, we need to build more than just individual great detectors. The other great thing about being in a tier 1 fab is that we can immediately scale up to manufacturing very large numbers of them. Our detectors are performing with near unit efficiency, and that's not just one-off hero devices. We have thousands of devices per wafer and hundreds of tested wafers, all performing with high efficiency and yield. The plot on the left shows the efficiency of over 200 devices, with 98% of the devices demonstrating greater than 90% internal efficiency. The plot on the right shows the level of process control across wafer to wafer, with a nanowire width variation of a nanometer and sub-angstrom control of the nanowire thickness. It's the advanced tools and rigorous process control and monitoring of the CMOS microelectronics industry that has enabled these high-performance devices. And it's this technology that will allow us to scale these devices to the millions of photon detectors required for fault-tolerant quantum computing. The microelectronics industry also excels at high-throughput testing, and we take full advantage of these routine tools. Using wafer-scale automated test and measurement equipment, we can perform thousands of measurements per day. And access to large data sets of statistically significant data is crucial for process and design optimization to engineer the higher performance and highest yield devices, as we have done here. And of course, the detector is just one example of the handful of integrated components that we have developed. And we have repeated this process for all the core photonic components: sources, filters, switches, etc. So far, I've been talking only about the photonic chip. Now let me say something about the full system. We've invested heavily in the control electronics, optical I/O, packaging and assembly that surrounds that chip, and that is required to scale to the building size machine we ultimately need. Here you can see our Q1 system, which is built around the silicon photonic chip that we have built at a tier 1 fab. In order to control and read out that chip, we sandwiched a standard CMOS chip directly on top of the photonics. In order to connect those two chips together, we have employed a wafer scale fusion bonding technique, which allows us to achieve hundreds of thousands of connections between the control chip and the photons. In addition to that, we have also enabled optical I/O to get both bright light and single photons in and out of the chip. We can now attach 200 optical fibers to the system using a high throughput industrial tool. Here's a closer look at that control chip. It's designed to run at cryogenic temperature and will control our single photon sources and read out our single photon detectors. This chip is built using standard 22 nanometer CMOS process. It has 750 million transistors and many thousands of connections through to the qubits. And here you can see what that hybrid wafer-to-wafer bond looks like, an entire 300 millimeter silicon photonics wafer bonded to an electronic wafer. Of course, in order to make use of our ability to do large-scale manufacturing, we need an architecture that leverages all the best features of a modular silicon photonic platform. And we have such an architecture. In addition to the hardware development that I've just shown you, our theorists have been working hard on the architecture. And what I'm most proud of is the serious effort that we have made to go from the types of ideas that you would see in a theory paper to a fully fleshed out recipe for a fault-tolerant optical quantum computer, which we have simulated in detail. Along the way, we have now improved the tolerance to error of architectures for optical quantum computing by more than 150x and reduced the footprint by well over 1,000,000x. This is all thanks to an approach that we are calling fusion-based quantum computing. You can find a detailed and pedagogical description of it in this recent paper, but let me give you a high-level overview. Photons are not qubits, and so the first step of an architecture for quantum computing is to define how we use photons to create qubits. There are different ways of creating qubits from photons, and the approach we are taking is to use a dual rail encoding. This uses a single photon in two photonic modes. A photon in the top rail is the qubit state 0, and in the bottom rail is the state 1. And there are a number of extremely compelling reasons to use this approach. Most importantly, photon loss is heralded. So loss is by far the most critical source of error in photonic devices. And since this photonic encoding has a constant photon number, all of this loss can be heralded at detection. The result is that extremely high loss tolerance is possible. Secondly, it is possible to put these photons through extremely long fiber delay lines, which itself is possible because the phase stability requirements between qubits is not too stringent. And finally, the quality of operations using linear optics is extremely high and intrinsic Pauli error is extremely low. So with this qubit encoding, we can perform arbitrary single qubit rotations with a simple interferometer, as shown here. But when it comes to entangling gates, the operations start to look very different to a circuit model. The natural entangling operation for photons is a fusion gate, which is simply a projective entangling measurement on two photons that can generate entanglement between two previously unconnected states. This operation is one of the two key primitives of our architecture. In terms of hardware, fusion gates are simply a beam splitter, which can be made with very high fidelity and manufactured in large volumes, as I've already shown you, followed by photo detection. While fusion gates do not generate entanglement deterministically, the non-determinism can be handled in a very simple way through quantum error correction. Our second architectural building block is the generation of small entangled photonic states. We can combine fusions to generate these entangled states. This is a probabilistic process, so we can take multiple copies and switch out successful events to create the states we want with high probability. The crucial thing here is that although this introduces an overhead, the resource states we need are constant size. They don't change when the computation grows. So the overhead in hardware is constant. That is, a larger computation means making more states, not bigger states. Running a larger and longer quantum computation also does not involve keeping any individual photon alive for a longer time. You can see this in this schematic where we see a full fusion-based quantum computation taking place on a logical error-corrected qubit. The resource states are produced at a high repetition rate in layers. Once produced, every photon is either immediately fused with its neighbor, or it is delayed by one clock cycle and fused with a later photon from the resource state generator. A beautiful feature of this approach is that the fusions can be adapted so that they complete both the measurements needed for error correction and the measurements needed for running an algorithm simultaneously. And of course, it is a great advantage that every photon is created and then used up rapidly, having passed through only a very small number of optical elements. So how do we know that it's going to work? Well, we know that it will work because we have built a multi-scale simulation stack to track over 25 sources of errors. These simulations begin with FDTD verified models of individual hardware components, such as directional couplers, detectors, and switches, which feed into second quantized simulations of small optical circuits. In turn, those feed into tensor network simulations of large layouts for resource state generation, which progress to capturing entire fusion networks. And finally, the decoding of non-trivial logical gates built from fusion networks. And the remarkable thing about this simulation stack, which has taken a team of over 20 people more than 2 years to create, is that we can now answer questions such as how varying some manufacturing performance parameter, such as the line edge roughness, will impact a logical gate on an error-corrected qubit. So what are the challenges for building a scalable machine? As I mentioned at the beginning, I'm very glad that quantum computing as a field is now at the point where anybody can build a qubit, and the big challenges to solve are about scaling to 1 million qubits. We're thinking about this in terms of 4 major challenges. On manufacturability, we have now seen for ourselves the incredible performance and reliability that is uniquely unlocked in a tier 1 chip foundry. It's our contention that this extreme level of process control is actually required to meet the scale and performance requirements of any fault-tolerant quantum computer. The flip side is that these industrial foundries will not allow exotic materials, atomic scale fabrication, and so on into their clean rooms. And we've found a way around that challenge in the form of our architecture. With respect to control electronics, we are now seeing great progress by Microsoft, Intel, and others, and this is really encouraging. You need millions of transistors to control and read out any practical quantum chip, and it's not viable long-term to be connecting the control chip to the qubits with coaxial cables. The control chip needs to be somehow packaged together with the qubits. On cooling power, any practical quantum computer is going to require a ton of cryogenic cooling power, not least to cool those control electronics which need to be proximate to the qubits. The only device in our system which needs to be cold is the superconducting single photon detector. Photons, of course, don't feel heat. And so we're lucky to be able to operate in the 4 Kelvin regime, where our current systems achieve watts of cooling power, thousands of times more than is available in the dilution refrigerators required for millikelvin temperatures. And finally, there's no way we're going to fit the quantum computer onto a single chip. Any quantum computer large enough to be useful will inevitably be an extensive system with many chips networked together. For matter-based qubits, that requires a transducer to convert from electronic quantum information to a photon and back again. We are, of course, in the fortunate position of not requiring such a transducer. We use telecom band single photons and can send these photons directly into standard optical fiber to connect chips together. And we've already demonstrated chip-to-chip teleportation and entanglement, for example. The challenge of cooling is a real one, but there is a world of difference between operating at a few Kelvin rather than a few millikelvin. PsiQuantum's chief development officer, built this multi-kilowatt cryostat at his last job. And there are hundreds of these systems on the planet, and we're pretty excited about getting our own one. In terms of large-scale networking, that will always involve communication between qubits using photons. And at optical frequencies, this lets us make use of the incredible properties of optical fibers. And I'd additionally contend that every quantum architecture ultimately needs to have the ability to move qubits between a large number of identical, clean, and simple modules. In our system, the encoding is already in photons, and so intrinsically compatible with fiber. Moreover, the FBQC architecture is also intrinsically highly modular. But there is another way in which the ready availability of low-loss fiber enables us to tackle the challenge of scaling, which is a new methodology we are calling interleaving. It is an exciting breakthrough that I am happy to be announcing to you today. As we saw previously, we can run the computation by generating a lot of resource states in every time step and then doing fusions. But rather than build a large number of resource state generators, we can also take just a single one and use variable length fiber delays to produce the same effective layout of fusions by a temporal rustering. This gives us over 1000x saving in the size of the machine we need to build. We call this type of temporal multiplexing interleaving, and details are in this archive preprint which appeared today. While temporal multiplexing is a standard feature of even classical communication, the key architectural feature we require is that we be able to do fault-tolerant logical gates without having to access the photons while they are propagating in the fiber. We have discovered that this is possible. The non-local, error-corrected topological gates we do can be performed without any kind of switchable memory. In fact, the photons undergo a fusion measurement as soon as they exit the fiber. This has big implications for keeping the number of optical elements every photon sees to a very low constant number. If we factor in acceptable amounts of fiber loss, then we find a trade-off given by this equation. One resource state generator plus 3 optical fibers equals around 5,000 qubits. Now, I'm an experimental physicist and I don't usually like presenting equations, but this one I'm very happy to present. And so to summarize, we've taken all of the real-world challenges to building a large-scale, useful quantum computer. And by we, of course, I mean this incredible team of people. And I'd like to finish by thanking the incredible colleagues that I've been working with over the last years. I hope there's some time for some questions. And indeed, I hope that you're poised to ask these questions, because I think these are questions that you should be asking of any quantum computing company, and you should be skeptical if their answers sound a bit too good to be true. So firstly, when will it be ready? Well, by the middle of this decade, we will have completely stood up all the manufacturing lines and processes necessary to be able to begin assembly of a final machine. Now, along the way to those fully manufacturable integrated quantum photonic systems, we'll be able to build some amazing devices which can generate a large amount of very interesting and highly pure entanglement. Some of this we hope to make accessible to you as scientists and of course to potential customers. Now, will those intermediate devices allow us to run quantum algorithms that will actually impact the world? No. For that, we need a full-size fault-tolerant system. And I would caution you against believing any claims that these truly valuable algorithms are only a couple of years away or can be achieved without fault tolerance, as there is currently no evidence that that is possible. That is why we are entirely focused on building a quantum computer with hundreds of logical qubits and billions of gates, which in answer to the second question is going to be a very large machine. As far as we know today, this is true for anyone building a quantum computer, whether you're using ion traps, quantum dots, or whatever. A fault-tolerant quantum computer is not going to sit on your desk. It is going to be a huge, extensive system, much like a data center. As you've seen, PsiQuantum's quantum computer will share many characteristics with a standard supercomputer or data center. thousands of silicon chips hooked together with regular optical fiber and aggressively cooled. It will also be manufactured using the same tools and technologies that are used to build the world's best and biggest supercomputers today. I think a good way to summarize the distinction between our approach and that of others is that rather than trying to scale a quantum process, we took a scalable process and have made it quantum. I'll leave it at that. And if you have any questions, please do reach out to us if you'd like to understand better the unique opportunities of the silicon photonic route to building a quantum computer.